Okay, let's get started. In this video we will talk about multi-threading. First of all, we will talk about what is it. We will talk about, multitasking, multi-threading. What's the difference? Is there a difference? And we will create some simple examples in C++, so you will see how it works. And then in another video we'll do some more advanced or real life use cases with worker task queue and so on. But let's start with what it is. Back in the days, maybe 50 years ago or so, there were computers. There was. And the users were connected to a single. The users didn't have a computer on their own. They just kind of had a keyboard and a screen, but no logic because all the logic. There was only one computer, in a single company. It could be like a single computer, and it was used by multiple users still. Let's have a look at this example here. I think this picture says a lot. So we have a single computer, and it works with a system called time sharing. So first, number one is allocated some CPU time. So now it looks like a he, right? This person is active, his program is running, and his keyboard is, the computer is allowing him to interact. And later it's time for number 2, and then it's number 3, and then it's number 4. So it's, every user is allocated a time slot. So it's a time sharing system, and if the computer can do this really fast, and if it's smart, and has some caching in place for input and so on, it could be done really well, actually. So the users won't even notice that they don't have access to the computer all the time. That sounds weird. How could it be? But that was how it was, and it's not that weird because it's still like this. It still is, but multitasking. The term multitasking, it's exactly the same. We have one computer, I should say, but a single user and multiple concurrent programs. So you are typically using a lot of programs at the same time, I would guess. Depending on if you have, how many cores you have, how many CPUs you have, I will talk about it in a minute, but typically you will have more active programs than you have, possible processing units on your computer. So probably your programs will be suspended for a short time and activated and so on, but you typically don't notice it. So that was time. Okay, so this picture, maybe it should have been here instead. Never mind. There are some problems, and we will talk about it when we start coding. Let's say we have 6. Let's talk about this problem. It's actually, it doesn't matter, but let's say we are 6 users or 6 programs. It's the same. The thing is, if person number 1 and person number 4 kind of simultaneously start printing a document, there will probably be a problem, because I mean, since it's interrupted, and then the next one and the next one, and so that would be, I mean, typically there would be like one line from user 1, and then maybe 5 characters for user 4, and then 3 characters for user 1 on the printout. So that's a problem. So when we are multitasking, we need to consider shared resources, and there are I have no idea what I've written. Okay, so I meant just one at a time. Okay, so the solution is to synchronize the access, and with that we could lock. I mean, now this cup mug is taken, so no one else could take it because I'm holding it. I'm not executing. I'm not sipping coffee right now, but no one else could take it because it's locked until I'm done. And if other people want to use my my mug, they have to stand in line, you know. Or we could have a queue, and a queue. We will talk about queues in the next video when we do a more, as I say, advanced solution with a task queue and worker threads. All right. Modern computers then. I mean, so in this scenario, there was just one processing unit, one CPU typically, and it had like, I mean, maybe 16 megs of RAM, and that was I mean, it was amazing mainframe computer in the early 80s. It could be like, seriously, we could not we I wasn't part of it, but there could be like thousands of concurrent users on that machine. It was so effective. Anyway, nowadays typically we have multiple CPUs and or multiple cores. So what is a core? A core is what we back in the days called a CPU. And it's the processing unit. So a core is, I mean, that's where execution takes place, and it has its own registers and its own cache, and I mean, that's where execution takes place, and then we have the CPU. The CPU typically have multiple cores nowadays. So a CPU kind of coordinate, actually not kind of, it does say it coordinates cores for the executing tasks in the computer system. So the CPU kind of decides which core to use for and for how long and so on. And as you can see, there are even, I mean, the cores have also, I mean, there are shared resources between the cores as well. Anyway, so that's the thing, that we, I mean, nowadays it is possible to really execute 2 or more things at the same time on your computer. I mean, we simulated it back here when we use a time sharing system. Nowadays it is possible to really execute multiple things at the exact same time. But actually it doesn't matter. I mean, for us, when we program it really, I mean, yeah, typically we should I mean, decide how large, for example, the thread worker queue should be, depending on how many cores we have on the system and so on. But typically it really doesn't matter, because when we create threads, I will talk about what a thread is. It's not like we can, let's say you have 4 cores on your computer. It's not like you can only create 4 threads. No. You can create basically as many as you like. So I mean, there is a thread is I mean, a thread, think of a thread as a task, and it will be time shared to the cores. It will be allocated physical, operating system. It will be allocated CPU time. So a thread is kind of an abstraction. It's not like it's continuously running. It could be. It could be if we, I mean, say on the ESP32, we have 2 cores, and in such a system we own all the resources. There are no, operating system things running in the background or anything taking our CPU cycles, so that it's possible to create 2 threads and have them execute all the time. But anyway, why would you like to use multi-threading? That's kind of important, because there are actually multiple use cases. First of all, it's a way to actually logically separate your code into separate tasks. And we talk about, I did talk about the embedded and ESP32. If you have multiple cores and tasks, it's really helping us separate your code into separate tasks, and it's really easy to write non-blocking code, because you could really block. You could write blocking code, because the ESP, the FreeRTOS, actually it is, the operating system will do the suspension and activation of the threads. Another, so it could lead to better code. Also, we have performance. So what do I mean by that? Splitting load to get done faster. Okay, so let's say you need to make, you need to cook, let's say 20 pancakes. And if each pancake takes 2 minutes, you will be done in 40 minutes, right? But instead, if you could split the load, I could come home to you and help you help you with the pancakes. So I can create 10 of them, and you can create 10 of them, and we will be done in half the time. If we could, get along at the same stove and so on. But you see what I mean. And actually, there might not be, exactly, we will typically not double the performance, because there are typically some shared resources we will fight. We will need to use the same things or appliances in the kitchen, maybe, and we have to wait for the other one, so we need to synchronize access to some of the things. But typically, it will get done faster. So instead of 40 minutes, it could be 20. Another use case is to appear more responsive. So let's say we have an application and you press a button, and when you press it, it will do some work, which will take like 10 seconds or so. Then you will have to, the program will not be responsive during that time. You can't, continue with another task. So that's another use case. And I mean, basically, these three are the most important use cases. And they will lead to, I mean, let's say any network server of today, be it a SMTP server, mail server, or web server or whatever, they are multi-threaded. And it's, I mean, what it means is that when we get a request, someone surfs to our site or whatever it is, we still need to be responsive. I mean, we can't just, okay, no one else could talk to us right now because I'm busy. So, I mean, typically we take the we take the request and put it into a background task and run it and still be able to serve more requests. So it's kind of like, oh, let me show you that one, what I mean. I'm just gonna start up my favorite diagram program, Excalibur. Just give me a minute. Okay, so let's say we have a restaurant, and this is the kitchen. And in the kitchen, I mean, there are stoves, and food is, we create food, and this is the table, and this is you. And now you come to the table, sits down, and you wait for the wait. And when the waiter comes, let me see. This will be the waiter. Actually, it's not a waiter. It's your servant. I will call it a servant right now. You will see why I call it a servant, or I don't know what to say. Anyway, so someone comes to you and asks, all right, what do you want? And you say, of course, pancakes. So what happens then is the servant goes to the kitchen and start making pancakes. During that time, I enter the same restaurant, and there is no servant. Why isn't there a servant? Because a servant is, I mean, is busy creating pancakes. So now the pancakes are ready after 40 minutes because you are hungry and you need 20 of them. So the servant brings the pancakes to you, and then the servant goes to the next one. As you can see, what we have here is one task, one thing, servant or whatever, handles the whole change. And during that time, there will be the restaurant will be unresponsive to new customers. There will be new customers, but they will be put on hold. So what we can do instead is we could create a queue. And the queue is, I mean, this is how all restaurants work. I mean, yeah. So we will have a queue, and the queue will be like the what we call them, the paper labels, you know. Okay. Anyway, so now let's call it the waiter instead. I don't know the correct word anyway. The waiter comes to you, asks, what do you want? Pancakes. Goes to the kitchen and put, you know, that white little label and says, okay. And after that, it will go to the next in line and have another. So now there will be pancakes and there will be pasta bolognese. So there are 2 orders in a queue, and the kitchen will serve these as fast as possible. What we are creating now, I mean, I hope you see, first of all, we are more responsive, but second, we also have, I mean, we have clear roles in our kitchen. So, I mean, a waiter is a waiter. Waiter knows what to do, has a single responsibility, and it's a lot easier also to I mean, okay, so we have a problem. We have a lot of food waiting in line here. So we could, I mean, we could create another kitchen, as in another thread, and but we still just have one waiter anyway. So that's the thing, how to think about the use cases and why we use multi-threading. And it's as I said, it's not all about, it's seldom about getting just the performance. I mean, if you have one thing you need to do, I mean, sometimes it's as long as it's not, I mean, involves a lot of CPU for a lot of time, like say 40 minutes or no, I don't know, 4 seconds. Performance will suffer from splitting into multiple threads, because there has to be synchronization. There is I mean, each thread will need their own stack memory and everything. So it's not like, okay, so we multi-threading and we make it faster. That's not the case. It's more like, okay, we're multi-threading so we can do other things while we wait. That's more the typical use case. Okay, so with multi-threading, you should think that, so you have your application, and when we run our application, typically we know exactly how it will run. It will start from line 1, 2, 3, 4, maybe jump into a function, there will be a loop, and so on. But the thing is, now there could be multiple executions at the same time in the same program. So that's the thing. And when you have multiple threads, as I said, we have a task scheduler, which will, I mean, say we have 5 threads in our program, and they will be interrupted, that is suspended and activated when the task scheduler finds it suitable. So it's time sharing, but inside our own program. And the thing is, each thread has its own state with registers, stack, could be variables as well. But one of the things that threads could talk to each other is by sharing variables. So let's just have a look at this stupid program. So we have a task doing work. And by the way, let's talk about, as you can see, we have this sleep. And we are using the literal const expression, so we can say 100 milliseconds, and it's inside the standard stud literals, chronoliterals, if you want to use just this one, because you typically don't want to use just using namespace stud. You know, that's an anti-pattern. All right, let's look. So what is it's? I mean, it's 100 times. It just says the prefix and whatever and sleeps. So when we run it, first of all, so we have this while loop, and it's some kind of administrative system. So you would think that instead of pressing 1, you press a button, and the thing is, when we press it, let's start it. When we press the button, so to speak, as you can see, it's completely unresponsive. So I can't do 2, or I can't do number 1, or I mean it's yeah. Now it's back, and now I could actually haven't even implemented 2 anyway. So that's the thing, and I think it's obvious what happens. Let's create another case. So there you saw how a program could be unresponsive, and I mean it's of course it's it's unresponsive. Let's do this instead. So now we have threads. The thing is, from C++11, threads are standardized inside C++. The reason why they did that was actually really important, because, as I say, most programs are multi-threaded today, because we typically write more and more, you know, network-enabled application and so on. So we are creating more and more multi-threaded programs, and since the C++ standard didn't even think about the concept, the thing threads, there would be problems like, let me just let me just create a sample why threads were added. One of the reasons, I mean, it's not the only, sorry, 100 and 100 and x++. I mean, this code, if we are, I mean, in a single threaded scenario, you would expect the compiler to be able to, I mean, this is completely waste. The compiler should be able to set it to, is it 15, right? And have a thread of 300, like this. I mean, this is what the compiler should be able to do, but it's not able to do it. Actually, now it's able to do it after C++11, because we have the notion of threads in the compiler. So the compiler, I mean, before that, it was undefined how it should be compiled. Anyway, so threads were added, and it's in this stud thread. So we have, and as you can see, we have it's a class thread, and what I am doing now, I'm creating 2 worker threads, worker 1 and worker 2, and we are sending in a pointer to a function. And we are also sending, as you can see, when the constructor for the thread is able to take, of course, not of course, but that's how it is, variadic parameters, because I mean we could maybe we want multiple things sent into this, so we could then add them like this. So anyway, as you can see, yeah, it's very erratic. Anyway, what happens now is we are creating two threads, and by default they are scheduled their starting execution right away. So just have a look at this. What happens? What we're doing now, what we're doing here is we are just joining, and that's a weird name, but think of it like this. What do you mean join? We are waiting for these two threads to finish. And let me explain the join. Think of it like this. So we have one thread. When the program begins, we have one thread, and then we branches. Worker 1 will be a branch from a current thread, and worker 2 will be a branch. And then we want to join them back into the same. That's how you should. I mean, I think in another program there are called. Is it wait? I don't remember. Anyway, so that's what we're doing. So we're waiting for them to finish and join back. Anyway. So I mean, this program is, yeah, we are doing two things at the same time, but we are not using the main thread for anything, but to wait for the other two threads. Maybe not the smartest, but I want to show you what happens. Okay, so let's start it, and as you can see now, it is. Okay, let's wait for it first. As you can see, it's, we have F and we have G, so we have, yeah, that was great. I couldn't even hope for better. As you can see, F, G, 0, 0. As you can see, even in this thing, what happened was, this first worker started and executed these two. I mean, it's the prefix. And then we can see that it was interrupted, and worker 2 ran and wrote G. So as you can see, it's completely random, but you can see here, I mean, here we have F98, G99, F99, and so on. But I mean, actually, it was pretty fortunate that we. I mean, that's what could happen. That's what could happen. And the thing is, we have completely, as you say, unpredictable output. If I run it again, let's have a look. Okay, so it was pretty much the same. Okay, but the thing is that doesn't matter. I mean, it doesn't have to be a problem that the output is non-deterministic. Probably it's not a problem at all, because typically you have different type of tasks that will take different time, or maybe the same kind of task, but it will take different amount of time. I mean, let's say you have two people going into a certain page on your website. I mean, one of them might be logged in, and you have to fetch the user info from the database, and the other one is not logged in, and you are not. So maybe one of them will. I mean, now we have exactly 100 milliseconds all the time. But I mean, it doesn't have to be like that. So I mean, typically you have a workload that is. I mean, it's diverse. The execution time, and that's where worker queues will come in handy later on. So this is the thing. we have threads, we have multiple things running at the same time. And let me just see if I should create another another demo already. Okay, so we have logic separation. We talked about it at least. We have performance, and we appear more responsive. At least we could appear more responsive if we would like that, because now these things are running on background thread. So we could have the menu run here instead. Yeah, so that's basically it. In the next video, I will show you another use case that is more advanced. As I said, we will then use a worker queue and task queue and worker threads, and that's how we typically create applications, network enabled applications today.